Welcome. Let's take a look at maximizing the area of a field. If you have 1,200 yards of fencing available, what is the largest rectangular enclosed field you can make if you only need to fence 3 sides of the field due to a cliff? So let's go ahead and start by making a diagram of the situation here. So we know that we have a cliff. So let's let this line be our cliff. And now we're trying to fence a rectangular field. So here's our rectangular field. 2 sides will be the same length. Let's let those be X. And one side will be potentially a different length. We'll call that Y. And if we have 1,200 yards of fencing, the 1,200 yards of fencing will be used to go around the perimeter of the field. So we know that 2x plus y has to equal 1,200 yards. Now, we're being asked to find the largest rectangular enclosed field. So this field would be largest if its area is largest. So we're interested in the area of this field. And the area of this field, because it's a rectangle, would be x times y. So what we're trying to do is maximize area, or x times y, subject to the constraint 2x plus y equals 1,200. So notice that our area function is a function of 2 variables. However, we do have this constraint that we can use to help us rewrite our area function as a function of 1 variable. It will also allow us to ensure the relationship 2x plus y equals 1,200. So let's go ahead and decide, do we want to replace x in the area function, or do we want to replace y? Well, looking at our constraint equation, it looks like it would be easiest to replace the y variable in the area function, because we would simply need to subtract by 2x on both sides of that equation. So y would equal 1,200 minus 2x, and then that would mean that our area function is x times 1,200 minus 2x. Then we can multiply that out, and we end up with 1,200x minus 2x squared. And so here's our area function that we want to maximize in this instance. Now, before we do that, let's think carefully about any constraints in terms of domain. So as I look at my domain function, if we have 1,200 yards of fencing, I could have the side labeled y be all 1,200 yards, or some smaller portion of that. So it's possible that y could be anywhere between 0 and 1,200. Now, thinking the same way for side x could be 0, in which case y would lie right along the cliff line, and x could go all the way to 600. It cannot go to 1,200 because we have 2 lengths of x. So 1,200 divided by 2 is 600. So x must be somewhere between 0 and 600. Okay, so now let's go ahead and look at maximizing our area. We'll start by finding the derivative. So a prime of x is equal to 1200 minus 4x. And now we need to identify critical points. We have two sources for critical points, the first being where the derivative is equal to 0. So a prime of x is equal to 0. The second being where a prime of x does not exist. Well, looking at our derivative here, it's a nice linear function and it's defined for all real numbers. So there are no critical points as a result of the derivative not existing. So let's come back to the first case. Our derivative is equal to 0. So we have 1200 minus 4x and we want that to equal 0. If we add 4x to both sides of the equation, we get 1200 equals 4x. And then if we divide both sides of the equation by 4, we end up with 300 equals x. So we have one critical number, or critical point. We have x is equal to 300. And now we need to think about verifying that we have indeed found a maximum. And given that this is a nice, easy function to find the second derivative of, the first derivative function, I'm going to go ahead and use the second derivative test. So a double prime of x is going to be equal to negative 4. And when I evaluate a double prime of x at 300, that is still equal to negative 4. So our second derivative is negative, which implies that we have a local or a relative maximum. In fact, it is the only local maximum for the function. Now there is one issue. We have this bound for our variables, and there could be a maximum at the endpoints. In theory, we're not expecting there to be one, but it is possible in theory. So we could also consider the area at 0, the area at 300, and then the area at 600. Now, using our area function, we'd have 1200 times 0 minus 2 times 0 squared. That will equal 0. Using our area function for 300, we'll have 1200 times 300 minus 2 times 300 squared, which is 180,000. And then we'd have area at 600, which would be 1200 times 600 minus 2 times 600 squared. And if we simplify that, we will end up with 0 as well. And that makes sense, because if x is equal to 0, then the entire length of the fence would lie along the edge of the cliff and there would be no area. Also, if x is equal to 600, the entire length of the fence would come out perpendicular to the cliff. There would be no width, and if there's no width, there would be no area. So we can make the conclusion that with 1,200 yards of fencing, the largest rectangular field you can make has an area of 180,000 square yards. I hope you find this helpful.